right, so I really like this problem. I think it's almost kind of fun. If I could call these thermal calculations fun, I really like this one. This is good stuff. We want to calculate everything. Delta H, delta S, delta G, and then we want to know at 25 degrees, will this reaction be spontaneous? I can't wait to find out. And I'm sure you're thinking the same, right? Now, often if you had to look up these numbers, delta H and delta S, like on a chart in the back of the book, it'll specify, it'll say, measured at 25 degrees Celsius and 1 atmosphere of pressure. And so I'll assume the same with these. The reaction below is carried out at 25 degrees Celsius and 1 atmosphere. The data in this chart would be corresponding. So eventually, to determine if the reaction is spontaneous, we need to know delta G. To know delta G, I need delta H and delta S. So let's just get after it, right? Delta H. Let's do that guy first. Delta H. Products minus reactants. So we're going to go 2 times that sulfur trioxide. Sulfur trioxide. Negative 396.0. And again, just for like convenience, I'll leave the unit out, but I promise I'll put them in at the end. That's my only product. Awesome. Minus reactants, 2 times the sulfur dioxide, negative 297.0. And then technically I should add the oxygen. But actually, how nice here, they give it to us, 0.0. Sometimes they may not do that. When I'm looking at heat of formation, pure elements should have a value of 0, as long as they're in their standard phase. So like oxygen diatomic in the gas phase is how it occurs in nature as an element. It does not take any energy to form the elements. They are naturally occurring. So if they left that out, just recognize that, oh yeah, that's an element. That would be 0. So we plug this in our calculator, and delta H is negative 198. Okay, so now here's the unit part. Technically, this means 2 moles. And then this guy, this negative 396.0, there it is. Whoopsie, 396.0. Backward. 96.0 is in units of kilojoules per mole. Okay, so I have like moles times kilojoules per mole. Moles and moles will cancel. And your unit is kilojoules. Okay, so the numerical value is all fine and dandy, but maybe what's more important is the sign of the delta H. The sign of the delta H is negative. That means this is exothermic. In nature, exothermic is usually spontaneous. Reactions that release energy are more likely to sustain themselves once they're started. So far we're looking good. Spontaneous. Okay, so let's do delta S. My buddy delta S. It's going to be set up the same way. Products, 2 times sulfur trioxide. So that is 257.0. That's my only product. Minus reactants, 2 times sulfur dioxide, 248.0, plus the oxygen. So now it's not 0. 205.0 for the oxygen. These are all gases, so again, their S values, their entropy values are all pretty high. Okay, so we got products minus reactants. We plug this in our calculator. And delta S is negative 187. And now for the unit. Again, if I were to take like a little snapshot here, this is 2 moles, and this 248.0, that's units of joules per Kelvin mole. Or sometimes they'll say like mole Kelvin. So if I cancel some of these like terms, moles and moles are out. So here's my unit. My final unit is joules per Kelvin. Ooh, negative. Okay, well, nature favors an increase in disorder, an increase in entropy. A positive delta S is more likely to be spontaneous. I have a negative. This is a decrease in entropy. Which, does that make sense? Well, everything's a gas, but yeah, I'm going from 1 to 3 moles of gas down to 2 moles of gas. So there's less total moles. That is not likely to be spontaneous. Nature favors an increase in disorder. A positive delta S. I have a negative. So we have opposing forces. You're at the seat of your chair, I can tell. The delta H, being exothermic, would make us think this is spontaneous, but we have a decrease in entropy, which is not likely to be spontaneous. In that case, the tiebreaker is temperature. Okay, so let's do delta G now, huh? Okay, so delta G, our equation, is delta H minus temperature times delta S. Plug and chug. These calculations really aren't that bad, right? Okay, so now here's the only thing that's super annoying. We've got our variables, and you'd think we should really just plug it right in, right? Kilojoules, joules. Be really careful with those units. I don't care which one you use, and they're not going to care on the AP test unless by chance they specify, like, calculate delta H in units of kilojoules or whatever. But if it's not specified, I really don't care which one you want to use, but they do need to be the same. So you either got to put both of them in joules or both of them in kilojoules. So I don't know. It really doesn't matter to me. We could maybe just, I don't know, let's take that delta H and say negative 198,000 joules. It really wouldn't matter. You could also use the second one in kilojoules. Minus. Here's the other thing we have to be a little careful of. Temperature. We're running this thing at 25 degrees Celsius. This value is for Kelvin. So when you plug this temperature value into your delta G equation, it does need to be in kelvins. So instead of 25 degrees Celsius, we're going to go 298 Kelvin. Then I can use my delta S, negative 187 joules per Kelvin. Okay, so easy, plug in your calculator. Blah, blah, blah. And we would have negative 142,000 joules. Which if you did it the other way, you'd have like negative 142 kilojoules. It really doesn't matter unless they specify. For a unit. Again, like watch what happens here. This is joules minus kelvins are going to cancel. So it's joules minus joules. So in this case, your final answer would be joules. Or you could have switched them both to kilojoules. So in the end, at this temperature, yes, we are spontaneous at 25 degrees Celsius. If you can do that, you are in a good place. We calculated delta H, delta S, delta G, and it comes down to temperature then. I would also understand like what these values mean. So I mean, everybody can plug it in their calculator, but what is the sign of the delta H, the delta S, the delta G? What does that mean, and how does that relate to the spontaneity of the reaction?